Now that we've developed some greater understanding of entropy and seen some of its relationships, I want to fill this out by adding some of the differential relationships that are going to matter for us. Now, I'll remind you that we have found that for, in general, increment of heat, that this is going to be less than or equal to TdS. It's going to be equal if the heat is reversible. Similarly, we have for work that it's minus P dV. So I can use these together actually to refine the expression that I have had for the internal energy, which remember was just the sum of the two incremental changes. I should have made that an incremental change as well. I can now write this as TdS minus P dV for reversible processes and for processes that basically are taking place at equilibrium. Now, the reason this is important is since internal energy is a state function, it doesn't matter whether I take a reversible path or some other path to do it. So I can use this reliably for a large number of different types of processes and still be able to get the right answer. Now, I do this because it tells me something about the functionality of the internal energy. In fact, this simple form tells me that natural variables for U would be entropy and volume. So if I think of U as a natural function of entropy and volume, I can actually write a total differential for U. So this is a total differential that would be du d entropy at constant volume ds plus the partial of U with respect to volume at constant S dV. But now I can relate that directly to the expression that I have here. It's equal to TdS minus P dV. And in particular, I can relate now this temperature to this partial derivative and the pressure to this partial derivative. So I actually have relationships that tell me what these partial derivatives are. Even though I don't know what the functional form of the internal energy is with respect to entropy, I know that its derivative is going to be the temperature. I also know that its derivative with respect to volume at constant entropy is going to be the negative pressure. Here, this tells me that internal energy grows as entropy grows, and this tells me that internal energy decreases as volume increases because it's equal to negative pressure, which is, of course, a negative number. So I'll make that less than 0, and this one is greater than 0. All right, so we can learn important facts about this even if we don't know what the functional form is. Now I could do something very similar for enthalpy, and remember that enthalpy is simply related to du plus dPV, which is going to be TdS minus P dV, and then the derivative here is going to be plus VdP plus P dV, and these two things cancel, so I find that entropy is TdS plus VdP, or in other words, I can think of enthalpy as being a natural function of entropy and pressure. So now when I write its total differential, I would write it something like this. I would write dH ds at constant pressure ds plus the partial of H with respect to pressure at constant entropy dP, and now I can relate it to this expression up here. So I can find that, for example, I'll have this is equal to TdS plus VdP, and that allows me to relate T is equal to the partial of enthalpy with respect to entropy at constant pressure, and volume is related to the partial derivative of enthalpy with respect to pressure at constant entropy. All right, so again, now I can see that enthalpy grows with entropy and with pressure. So it helps us to learn something about these functional relationships that can be useful as we look more at these functions without necessarily knowing what their functional form is.